We're going to continue solving systems of linear first order equations. And I want to make a clarification. The clarification is that our focus is on homogeneous systems. Okay. So in the last video, we looked at a case where the two systems have distinct eigenvalues, and the two equations involved in the system have distinct eigenvalues. And I gave you a problem to try where there are three equations. So today we're going to look at the case where they have repeated eigenvalues, and if we have time, we'll also look at a case where they have complex eigenvalues. I want to go back to the last time and look at the phase plane before we continued. If you look at the last video, I detailed how to get this phase plane, and I said that if we have this case, the fixed point over here, 0, 0 is the fixed point, and this fixed point is called a stable node or a sink. All right. I didn't specify the name for the fixed point in this particular situation. So if you look at this, the arrows are pointing inwards. You can go back to the video and see why they're pointing inward. And in this situation where both eigenvalues are positive, as opposed to the both eigenvalues being negative here, when both eigenvalues are positive, the arrows point outward. And in this case, the fixed point is called an unstable node or a sink. Unstable node or sink. All right. And I talked about when we have two eigenvalues, one negative, one positive, we get what we call a saddle node or saddle point, actually. Again, you can go to the previous video and refresh your memory on how we got those. Okay, today we're going to look at a case where we have repeated eigenvalues. So let's say systems with repeated eigenvalues. Okay, so maybe I'll call this example 4. No. What do I call it? Let me call it example 3. Example 3. Okay, so let's solve the system. The x dt is equal to x minus y, and dy dt is equal to x plus 3y. So again, we can write this as dx dt is equal to 1, negative 1, 1, 3, and then we have xy. This is our a, call this our a, and this is our x, and this is our dx dt. All right, so let's look for the eigenvalues. So for the eigenvalues, we need to solve the system lambda squared minus trace of a lambda plus determinant of a is equal to 0. So this implies we have lambda squared. Trace of a is let's see, trace of A is 4, so minus 4 lambda. Determinant of A seems like it's also 4 plus 4 is equal to 0. If we factor this, we should get lambda minus 2 equal to 0. So our eigenvalue is lambda is equal to 2 twice. So let's look for the eigenvector. We're going to end up just having one eigenvector, and we're going to manipulate that to get two eigenvectors. I'll show you how. So for the eigenvectors, we need to solve A minus lambda I V is equal to 0. And this amounts to, if you do this, you end up with negative 1, 1, 1. V1, V2 is equal to 0, 0. And this is the same equation. So we just end up with V1. If we go with the second equation, we just end up with V1 plus V2 is equal to 0, or we have that V2 is equal to negative V1. So this means that our eigenvector is, let's make V1 1 and V2 be negative 1. So that's our eigenvector. But we need two eigenvectors for linear independence. And to get the second eigenvector, we look for what we call a generalized eigenvector. So we want a generalized eigenvector. And what is that? Our generalized eigenvector, we're going to call it W. And how to solve for it is this. You want to solve A minus lambda I. Want to solve A minus lambda I W is equal to V. You want to solve it for W, okay? So our A minus lambda I is, this is our A minus lambda I right here, this, okay? So you want to solve negative 1, 1, 1 times V. Your V is 1, negative 1, no, times W, sorry. W1, W2 is equal to V is 1, negative 1. Okay. So remember, this is A minus lambda I is that. So this is your A minus lambda I, this, times W, then is equal to V. So if you solve this, you end up with two equations. The two equations are negative W1 minus W2 is equal to 1. And then you have the next equation is so W, or you have W1 plus W2 is equal to negative 1. So it's like the same thing. So we just go with one of them. So this tells us that W2 is equal to negative W1 minus 1, right? So if we let W1 be equal to K, then W2 will be equal to negative 1 minus K, okay? And this will let our W, our vector W, which is W1 and W2, so let's write it W1 W2. We can write it as W1 is K. So I'm going to write this plus K here, and then I'm going to fill in the gap. So W1 is K, so that's 0 plus 1 times K. That's how I'm going to write it. And W2 is negative 1 minus K, so I'm going to put negative 1 here, and then I'm going to put negative 1 times K. One thing I want you to notice is that this right here is our V. So if you do it well, you always end up with your V. All right? So this is what you're going to take away from here. Okay? Let's call this U and call this V. Okay? So our solution here, general solution in this case, so we have one eigenvalue and we found one eigenvector and an associated generalized eigenvector. So the general solution in this case is going to be x of t is equal to C1 e to the lambda t times v plus C2 t e to the lambda t times v plus e to the lambda t times u. So that's how the answer it's supposed to be. This is the solution when you have a generalized, when you have a repeated eigenvalue. So in our case, our general solution now becomes, that we're looking for, now becomes x of t. No. Is C1 e to the, our lambda is 2, e to the 2t times v. What is v? V is 1, negative 1, plus C2 t e to the 2t times, let's expand it. I'm going to write it like this. C2 t e to the 2t times 1, negative 1, plus C2 e to the lambda t times 0, negative 1. So that's our solution. And of course, you can split it into two solutions. All right. Let's try to get a phase portrait for this. Okay? Let's go for a phase portrait. All right, what's our phase portrait gonna look like? We're going to start with the eigenvector, the one eigenvector that we have. So the eigenvector is 1, negative 1. Okay? So we have 1, negative 1. So have this point over here. We're going to try to connect a line. All right. So our eigenvector lives on that line. And then we're going to do something because we have just one eigenvector, and that eigenvector has values. We have just one eigenvalue, and that eigenvalue is positive. Okay, so since it's positive, the trajectories are going to be pointing out this way. Okay. And another thing we know is that the origin is a fixed point. In this case, the origin is an unstable fixed point, an unstable equilibrium, if you may. So, trajectories are going to be trying their best to be parallel to this eigenvector and at the same time asymptotic to the eigenvector. So let's see what that means. That means that if you have a trajectory that starts over here, it's going to become a little bit asymptotic to our eigenvector. Then all of a sudden, it's going to be pushed away because the eigenvalue is positive and it's going to start to go out of here. Okay. So same thing would happen for like that. It's going to go like that. And then a similar thing would happen here. Okay. And like that. All right. So you might be asking, why is it not the other way around? The quick answer to that is you can figure out which way it is by picking a point. Let's say you pick a point, let's say you pick 1, 1. Pick the point 1, 1. 1, 1 should be over here, maybe over here, something like that. Oh no, over there. Okay. And you want to go plug 1, 1 into your equation, into this equation. So at 1, 1, x1, y1, dx dt, dx dt is actually 0. Dy dt is equal to 4. So what does that mean? 0 and 4. That means that x is not increasing, but y is increasing at the rate of 4. So my sketch is almost there. So what my sketch was supposed to do was this trajectory is supposed to maybe go like this, all right? Because x is increasing at a positive rate. Meanwhile, y is x is not increasing, but y is increasing at a positive rate. All right. So that means I need to do some correction, not too much, but just a little bit of correction. But the general behavior is still the same thing, because if you keep going, at some point, this graph is gonna, you know what? I think I was almost right the first time. Let me see. What do I have here? Let me see. This is my 1, 1, maybe here. So I'm going to go like this. I'm going to go like this, like that. And then I'm going to gradually go that way. See? So I'm kind of right. And then I'll have something similar. Okay. So my point of picking those values is to just see which way is it going. You know, which way is x? How is x increasing? X is not increasing at that point. Meanwhile, y is increasing. Okay, so that's how you get it. All right. So this kind of fixed point, this kind of phase portrait, the eigenvalue is positive, so trajectories are moving away from the fixed point. This is called an unstable, improper node. Okay. It's also called unstable degenerate node. All right. Now, it could also be that we have one fixed point or one eigenvalue, I mean to say, and this eigenvalue is negative, right? if this eigenvalue is negative, then the only thing, assuming the eigenvalue was negative 2, then the only thing that would change is that these arrows are going to be pointing inwards now, inwards, right? And our fixed point will be stable. And in this case, it's going to be called stable stable improper node. Improper node. So this is if eigenvalue is equal to negative 2. Say it's negative 2. All right. Okay. All right, so I think I should stop here, but I'm going to make another video. Leave a comment. I'll see you in class. All right, bye.